Today we are going to look at polynomial regression. So we've already done linear regression, but the question is, what do we do if this is a polynomial of degree 2 or higher? Okay. And specifically today we're going to look at a polynomial of degree 2. Okay. And let's see what that polynomial looks like. Since it is of degree 2, that's why we have a quadratic here. And we'd like to figure out a0, a1, and a2. That's our goal. So that it most closely fits our data. And we're going to do that by actually looking at the square of the errors here. So I need to put a little 2 up here. There we go. The sum of the square residuals. All right. Okay, let's go ahead and take our first partial. Let's go the partial of Q with respect to a sub 0. Okay. So if we were to do that, we'd get the sum from I equals 1 to n. We bring that 2 down, and if you want to, you could bring that 2 all the way out front. That would be fine too. Okay. And then we'll have y sub I minus a sub 0 minus a1x sub I minus a2 x sub I squared, and then this would all be to the 1. And since we're differentiating with respect to a0, we'd also need to multiply all this by minus 1. So I'm just going to make myself a little more space here and insert that minus 2 right in front of the sum. There we go. There's room for our minus 2 now. So there's one of them. Okay. Let's take our partial with respect to a1. Okay. So for a1, again, we'll have a negative here again, and a 2 that'll come out front. So I'm just going to write that out front right off the bat. Minus 2, the sum from I equals 1 to n. And now you might be wondering, well, if I were to say just differentiate this term right here with respect to a1, I'd actually not get minus 1, but I get minus xi. Okay. Well, I can't pull the xi outside of the sum, okay, because it has i's in it, okay, meaning that those x's change as this I changes here in our sum. So I can't bring that out front. So I'm going to have to just leave it here in the sum. And then we'll still have our y sub I minus a sub 0 minus a sub 1 x sub I minus a sub 2 x sub I squared, and then all to the 1. Okay. But remember, the derivative of the inside using the chain rule would have just been the derivative of this piece here, which would be minus xi with the addition of this 2 that we brought down here. And so you can see we have the minus 2 and we have the x sub I all here. Okay. And let's take one more partial. Okay. Our partial of q with respect to a2. Okay. And once again, a 2 will come down, a negative will come out, so I'll have minus 2 times the sum of I equals 1 to n. Okay. But this time the thing that was in front of a2, or next to a2 I should say, is x sub I squared. So it's going to put an x sub I squared out front here, and then of course we'll have all the same stuff in here. Now the question is, what are we going to do with this? We have our 3 partials here. Well, we're going to set these things equal to 0, and we're going to try to break these things up a little bit. Okay, but yeah, these are our 3 partials here. All right, so let's go ahead and set them equal to 0. So 0 equals. And also note, since all these have a -2 in front of them, after you set them equal to 0, you can just divide both sides of the equation by -2, and you'll get rid of those -2's there. So I'm not even going to write the -2 in there. Okay, but let's move on to the sum. Okay, so we're going to have the sum. And I'm going to split our sums up into multiple pieces, and there's a good reason for it. Okay, so there's our first sum, and then we have another sum. Okay, and this one's of A0. And this one's A sub 1 x sub I. Okay. And then a minus a sum from I equals 1 to n of A sub 2 x sub I squared. Okay. And I think I'm just going to pause the video for a minute and write in these next 2 equations broken up like this. You can try it yourself here and pause the video too if you'd like. All right, so it's all in here now. We've set all 3 of these equal to 0. Okay, and we broke up all the sums and we divided each side of each equation by -2. And it's given us these 3 equations here. And one easy mistake to make as you were writing these equations is forgetting that there, say, was this x sub I here and x sub I squared. Okay? And that's the reason that you can see as we go down from one equation to the next, we have higher powers on the x sub i's. Okay. But now the question is, well, what do we want to do now? What do we do from here? Okay. Well, we are going to want to move some of these terms over. I want you to notice that the first sum in every equation does not contain an A0, an A1, or an A2. It doesn't contain any A's. So we're actually gonna move those to the other side of the equation. Okay. Let's go ahead and actually, rather than moving those, why don't we move everything else other than those? So we're gonna move, for instance, this stuff right here over to the left-hand side, and so it'll all be positive now. Let's go ahead and do that. I'm going to pause while I write it out because it's probably not going to be exciting to watch me write it. Okay, our sums have been rearranged. Again, you can see all these terms that had a minus sign in front of them, they've been moved over to the left-hand side. Okay. And I did something else too while I was at it. I brought out A1, A0, and A2 outside of all these sums. And so is what this should starting to be looking like is actually a 3x3 matrix. Okay. Let's do that as our next step. Let's convert this into a matrix. Okay. What would that look like? Let's see. So our matrix we're going to need to make kind of big so that it can fit these sums in it. Okay. See if that's good here for now. So I want to point out what this sum here would be before I go and write it, and actually without the a naught though, without the a naught, just this sum from I equals 1 to n, okay, that's just going to add 1 n times, okay, so that's going to be n, okay. That's kind of nice. Let's go to the sum below it. That one we're not going to be able to do anything kind of clever with there, so we'll just go ahead and say the sum from I equals 1 to n of x sub I, and the one below that would be the sum from I equals 1 to n of x sub I squared. But remember, all these things in these sums are just a bunch of constants that we're adding together. So these sums will just wind up being a number in the long run here. All right, and let's get in the next sum. You can see it has an a1 in front of it, but I'm not going to write that. I'm just going to write the I equals 1 to n of x sub I. And below that should go the sum from I equals 1 to n of x sub I squared. And below that should be the sum from I equals 1 to n of x sub I cubed. And we're getting close onto this last column here of this matrix. Is going to be the sum from I equals 1 to n of x sub I squared. And you can imagine as we work our way down, these powers are just going to increase. So x sub I cubed, and then finally x of I to the fourth. Okay. Now you might be wondering, well, what happened to, you know, A0 through A2? And those are just right here, A0, A1, A2. If you were to multiply that matrix by this vector, you'll get the left-hand side of these three equations. Okay, but of course we still have the right-hand side. So for the right-hand side, we have the sum from I equals 1 to n of just y sub I. The sum from I equals 1 to n of x sub I, y sub I. And then the last one. So x sub I squared times y sub I. So what we're going to do here is we are going to create this matrix. And let me be specific about this matrix, even though I think you have a pretty good idea which one I'm talking about here. We're going to make this matrix in Matlab and this vector in Matlab. And to find these, we'll just use a \b. Okay? That's what we're going to do. And we'll go ahead when we're done and we'll plot our results and all that and see if it worked out just fine. Okay? But this is the idea. And if you wanted to fit your data to a cubic, your matrix A would be a 4 by 4. Okay? And your vector B would be a 4 by 1. Okay? And so each time you go up a degree for the polynomial, the size of your matrix is also going to go up. Okay? So let's go ahead and switch over to Matlab. Let's begin by importing our data here. And we're just going to use that coronavirus data that we were looking at the other day here. Okay, so let's go ahead and hit home and then import data. And I am going to input this coronavirus cases data. Okay. And you can see it's highlighted more than we want it to. Okay, we don't want those actual dates in there. That's going to mess up our calculation. And just like the titles would mess up our conversion from a table to an array. So I'm just highlighting the data we want, the week, and the total number of cases. Okay. All right, well, let's go ahead then and hit import here, and it imports quickly. You'll see a little tiny message pop up. You can see the following variables were imported. So once that's done, you have to click this X here to get back. Okay, so now we're in. Okay. And I want us to do, again, the same thing as yesterday. We're going to start off with data equals table to array. Because, again, our coronavirus cases, let me actually write that. That data is as a table, and we need it as an array if we want to be able to work with that data. Okay. So that's taken care of. Let's separate the X data from the Y data, just to make it a little easier to work with. So the first column is actually going to be the week. Okay. So let's say all rows, first column, and for Y, we'll do all rows, second column. Okay. And we did take a look at this yesterday, but just so that we have it for when we actually fit our data to a quadratic, we have something to compare to. Let's do X comma Y. Okay. And we'll go ahead and we'll plot this right now, just as a reminder of what this data set looks like. And you'll see that it probably does look a little bit more exponential, but for this short time period, an exponential or a quadratic are probably going to fit this pretty similarly. Okay. Let's go ahead and run it. So I'm going to need to hit editor and run. And you know what? I want to make this an asterisk so that way we can see each data point. There we go. So right, that looks a little more exponential to me, but we're going to fit a quadratic to this. So as what we need to do is I need to pull up my OneNote on the side and then this, and we'll try and generate those matrices, or that matrix that we were looking at. All right, here we go. So let's start actually starting off with a blank matrix A and blank vector B. Okay. So we know that A is going to be filled with zeros to begin with, but in the end, it's going to be filled with these sums. So this is just our beginning A. We're going to continuously keep adding things to A over and over until we've generated the actual matrix A. Okay. So I have a 3 by 3, and we'll do the same thing for B, but B is just a 3 by 1. There we go. And the next thing we'll do is we'll start a for loop for I equals 1 to what? Okay. Well, the number of data points we have. Why don't we just say n is equal to the length of x, okay? And remember, the length of x should match the length of y, okay? Otherwise, when we went to plot this, it would have been upset if they were actually different lengths, okay? So it doesn't matter which one I chose to designate the n is what I'm getting at, okay? So we have the beginning of our for loop, and the next thing we'd like to do is we would like to generate, again, that matrix A. So I'm going to write A equals, and so if we're going to be summing n times here, well, then for this upper left-hand entry where you see the n in the blue matrix, well, we just need to make that a 1. It's going to add 1 n times, which will give us n. Okay. And then for our next spot in here, I'm going to make a little bit more space maybe in here. Our next one would be x of I. So this is going to keep adding. It'll add x1 plus x2 plus x3 and so on. And then we want x of I squared. And that's the end of the first row. But I'm still going to make a little bit more space here, and it's because we're going to have a couple things that are squared and cubed and raised to the fourth in here. But since that was the end of our first row, I'm going to put a semicolon there. And then to begin our next one, we'll have an x of I. Okay, and then our next one after that is going to be x of I squared. And then the next one will be x of I cubed. Okay. There we go. And then on to our next row. And it looks like this next one starts with x of I squared, and then x of I cubed, and then x of I to the fourth. Okay, and let's just space all this stuff out so we can see it just a little bit better. Okay, yeah, I think that's a little bit easier to look at. And we want to add a to it. So a starts off as just zeros, but every time this for loop iterates, we'll be adding all the previous a's to this. Okay. Again, in other words, it's going to keep adding the x of i's until we've added all of them, all n of them. And the x of I squareds, it'll keep adding those until we've done it with all n of them, and so on. Okay. So here's our for loop that generates A. We're going to need one that also generates B. Okay. So B equals. So B equals, and let's start that thing. And I'm going to move this over a little bit so we can see what the B vector looks like. The first thing was the sum of y sub I. So y sub I, and then x of I times y of I, okay. And then the last one should be x of I squared times y of I, okay. And so that ends that. We just need to add the previous b to it each time. Okay. And let's suppress that. Let's suppress this. And we will move down to the next line. We will end the for loop, because that's going to generate our matrices A and B. Okay. And now this is going to give us those A's we were looking for. A0, A1, A2. So let's just maybe call it A. So A equals big A backslash B. Okay. This is going to be the vector containing our coefficients. Okay. So next, note that our X values in this coronavirus data go from week 0 to week 10. So when we go to try and plot this polynomial that we're going to create here, let's try and go from 0 to 10. But let's make sure we have enough points in here to make it smooth. So let's try 50. Okay. And I'm going to call this big X. Okay. And let's start creating our quadratic. Okay. But we need to remember if A0 was the constant term, or if that was the term that went with the x squared term. Okay. Let's scroll up here. Okay. Here we go. So you can see that it is a sub 0 that is the constant term, and a2 is what's going to go with x squared, and a1 is what will go with x. So we could do a of 0 plus a of 1. And actually, my indexes are a little bit different, right? We can't index a vector, or we can't start a vector with an index of 0. It starts with a 1. So this should actually be a of 1, a of 2, which will multiply by x plus a of 3, which will multiply by x squared. Okay. And we're plugging in a vector here, so I should put the little dot here in front of this caret. All right, and let's suppress this as well. Okay. And we are just going to go plot big X, big Y, and let's go with red. Okay. And so hopefully this looks like it fits our data decently after we hit run. Okay, and so it doesn't look like it because I didn't ever type in hold on. Let's go include that up here. There we go. So even though this probably should not have been fit with a quadratic, it's not doing too bad of a job. Okay. All right. And is what we'll see tomorrow is that this technique that we just used, we can use this technique actually to solve many other problems. In fact, tomorrow we'll try and maybe fit a plane to a set of data. So rather than a line or a polynomial, okay, we'll actually try and fit a plane to a set of data. Okay. All right, that is it for today.